The problem is from GATE 2015 Mathematics paper, question number 47. The problem given is, let M be an invertible Hermitian matrix and let x comma y in R. R is real number, the space of all real numbers, be such that x square is less than 4y, which is strictly less than. X square is strictly less than 4y. Then the four options given are: option A, both m square plus xm plus yi and m square minus xm plus yi are singular. Option B, m square plus xm plus yi is singular, but m square minus xm plus yi is non-singular. Option C, m square plus xm plus yi is non-singular, but m square minus xm plus yi is singular. And option D, both m square plus xm plus yi and m square minus xm plus yi are non-singular. So it is given the only hypothesis as M be a invertible Hermitian matrix, and for the variables x and y in real numbers with the condition x square is less than 1, which one is singular among these two matrices, m square plus xm plus yi and m square minus xm plus yi, which one is singular, which one is non-singular. So the NPTEL reference to solve this problem is module 7 lecture 26 with the title Eigenvalues and Eigenvectors of Linear Operators, from the topic Linear Algebra by Dr. K.C. Shivakumar. He is from Department of Mathematics, IIT Madras. Even you can watch this reference video using this YouTube link. So now coming to the solution. To solve this problem, one should know one thing about the given kind of matrices. Since here it is given invertible Hermitian matrix, that is M is invertible Hermitian matrix. So to solve this problem, one should have some idea about these Hermitian matrices. So it is given invertible. So from this we can observe that determinant of M is non-zero. And it is also given that for x comma y in real numbers, it is given x square is strictly less than 4y. So based on this condition only, all the four options are dependent. So let me explain one. Okay, firstly, let's consider what are the matrices given. It is given m square plus xm plus yi, and one more matrix m square minus xm plus yi. So for these two matrices, we have to consider, we have to check whether which one is singular and which one is non-singular. So for that, so we solve this problem by using the eigenvalues topic. So for invertible Hermitian matrix, we know, for the Hermitian matrices, we know Hermitian matrices are the eigenvalues of Hermitian matrices. Eigenvalues of Hermitian matrices are always real. That means, since here it is M is given Hermitian matrix, all of its eigenvalues, all eigenvalues of M are real only. So now, considering this statement, we check which one among these two matrices are singular for this condition. Suppose the first one is singular. Suppose m square plus xm plus I is singular. That means then we have then we have 0 is one of its eigenvalue. Then 0 is one of its eigenvalue. Hence 0 has to satisfy its minimal polynomial. So here it is yi. So 0 has to be one of its eigenvalue. That means 0 has to satisfy this condition. That means, but from the given condition, we can see x square is less than 4y. And we can see for any real number x, we can see x square is always greater than or equal to 0. That means always y has to be greater than 0. So, but whenever we have this is singular, we have 0 is one of its eigenvalue. That means, and we have that whenever we have an eigenvalue that has to satisfy each of its annihilating polynomial. But here, this eigenvalue 0 does not satisfy this annihilating polynomial. Why? Because if we substitute 0 in this polynomial, we can see we get yi. But for this condition, we have y is always greater than 0. So for any y greater than 0, we have yi is not equal to 0. So, but 0 does not satisfy m square plus xm plus yi. Or let me write this as a polynomial. Since we are speaking about the scalars, so let me write this as some capital X square plus x capital X y. So does not satisfy this polynomial as a polynomial. For these conditions, if we have y is equal to 0, then we can say 0 satisfies this polynomial, and in that case one can say this matrix can be singular. But for this condition, x square is strictly less than 4y, we always have that y is greater than 0. Even if we have x square is less than or equal to 4y, in that case we can see y can be 0. If we have if we have less than or equal to here, in that case we can see y can be greater than or equal to 0. And for in such cases, we can say 0 can satisfy this polynomial. But here, when it is given strictly less than, we can see 0 does not satisfy this polynomial for any y. So this polynomial is non-singular, since whenever we have 0 as eigenvalue, it has to satisfy the annihilating polynomial. So this matrix is not singular. So m square plus xm plus yi is non-singular. Similarly, m square minus xm plus yi is also non-singular, which follows in the same way. Suppose we consider this matrix as singular, then we have 0 as its eigenvalue, and again we have, in that case, y is also has to be greater than 0, but 0 does not satisfy the same polynomial when we take minus here. Instead of plus, we have minus for this corresponding matrix. So in both the cases, we have these two matrices are non-singular. This is one way, and let me explain another method also. So this is method 1. So let me explain one more method also. Consider the polynomial x square plus or minus x capital X plus y. So whenever we have to look at the zeros of this polynomial, as we can see, this is quadratic expression. So for the zeros of this polynomial are nothing but are x equal to minus x plus or minus square root of b square x square minus 4y divided by 2. And we have that for x square is strictly less than 4y, we have x square minus 4y is strictly less than 0. So for this we have then x is not real, and in fact it becomes complex complex number. So when we consider this polynomial, we have the roots of this polynomial are purely complex. In any way this cannot be real for this condition, but here for for the given matrix M, it is given Hermitian matrix, and we know for Hermitian matrix the eigenvalues are always real. But when we have this as the polynomial, we can see this is nothing but in the form of our given two matrices m square plus xm plus ya, m square minus xm plus ya. So when we say m satisfies this polynomial, then the roots of the eigenvalues of m has to be real. But when we have but here for this corresponding polynomial we are getting the roots are complex numbers. So we can say m does not satisfy this polynomial, and hence 0 is not an eigenvalue, and hence the matrix is not singular. I am speaking about corresponding to each matrix separately. So we have both matrices are non-singular, hence option D is correct.